Welcome to Chapter 7, Part 2, our continuation of the mole. We're talking about chemical quantities. In Part 1, we introduced the concept of the mole, and now in Section 2, we're going to talk about what we can do with moles. We can talk about mole masses and mole volumes. So we're going to use the mole to change between mass and volume and count. In Section 1, we learned 3 new terms to represent moles of different substances. So gram atomic mass, which is just the atomic mass in grams. Gram molecular mass, which is the molecular mass in grams. Or gram formula mass, which is the formula mass in grams. These would pertain to elements, these would pertain to diatomic molecules and other molecular compounds, and these would pertain to ionic formula and ions. But there's a term that covers all 3 of these, and we're going to use this more generic term unless we need a more specific term. And that is molar mass. So when we talk about molar mass, we'll be talking about gram atomic mass, gram molecular mass, and gram formula mass as a more general concept. So molar mass means the mass in grams of 1 mole of any substance, whether that substance is an ionic substance or an ion or a molecule or an element, an atom. So if there's a chance of confusion, like we ask the question, what is a mole of oxygen? Then you could say, well, wait, it's confusing. Do you mean in its natural diatomic form, or do you just mean as a single atom? And so we might have to distinguish there whether we talk about the molar mass of the molecule or the molar mass of the atom. So in that case, we'll use a more specific term, but otherwise we'll use the more general term molar mass to refer to the mass in grams of any substance. So we can replace those other terms, GAM, GAM, and GFM, with just molar mass. Now, with liquids and solids, the volume of a mole can vary widely. So here are some pictures, and each of these has a mole. Here's a mole of sugar, which is a very large molecule, so as you might expect, it's going to take up quite a bit more volume. Here's a mole of copper. Here's a mole of sulfur. Here's a mole of sodium chloride, good old-fashioned table salt. And notice that it must be a much smaller ionic formula than sugar, because they each have the same number, right? They each have Avogadro's number of representative units, but these units must be bigger because a mole of them is quite a bit bigger. So my point basically is that liquids and solids can vary widely. Remember how small a mole of water was. Just 18 grams, just over an ounce of water, is a mole of water particles, molecules. But when it comes to gases, happily, there is very little variation. When it comes to the volume of a mole of a gas, it doesn't seem to matter what the weight of the individual particles are, gas particles. They all weigh about the same. So here are a bunch of 2-liter bottles. So the volume of 11 2-liter bottles would be 22 liters. And that is just essentially the volume of a mole of gas at what we call STP, which is standard temperature and pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere, which is basically sea level air pressure. And so any mole of gas at that temperature and pressure is 22.4 liters. And it doesn't matter if it is a very dense gas, heavy gas, or it's a very light gas, very undense, it has a very low density. The density doesn't matter. The density affects the weight, so a balloon of a dense gas would be heavier than a balloon of a very non-dense gas, but they would still occupy the same volume. So this quantity, 22.4 liters, is known as the molar volume of a gas. So they can have different weights, but at standard temperature and pressure, they will have the same volumes. So here's just some representations. So a mole of nitrogen gas would weigh 28 grams. Remember, it's a diatomic molecule. These are all diatomic. Oh, not this one. A mole of hydrogen is going to weigh 2 grams, a mole of oxygen 32 grams, a mole of helium only 4 grams, but they're all going to take up the same amount of volume. So that finishes up what we can do with the mole. But now I want to just combine all of our concepts. Just like with apples, right? We could use the term dozen to connect count and volume and what was the other thing? Anyway, the same way, all paths lead to and from the mole. So here's the mole roadmap. So from any one of these, so we could start with the weight of something. Let's say I have 12 grams of carbon-12. Well, I know that 1 mole is equal to 12 grams, so that gives me 1 mole. And with that mole, I know that every mole is worth 6.02 times 10 to the 23rd particles, Avogadro's number. So I can go from weight to mole, mole to individual count. Or I can go from, let's say I have a gas, I can go from the weight of the gas, let's say 32 grams of oxygen, that is a mole of gas, and that gives me 22.4 liters of gas. Or I could say, listen, I've got 22.4 liters of gas, which is a mole, which is this many particles. So in my balloon, my giant balloon full of 22.4 liters, I've got Avogadro's number of particles. Or I've got the mass of a mole of diatomic oxygen, which is 32 particles. So we can convert between volume, mass, and count. That's how we measured apples. Remember, we did the same thing with apples. So, we could buy them by the count, we could buy them by weight, we could buy them by volume, and we related all 3 of those to the common term dozen. Remember, and now we can do the same thing with the same relationship between a mole. We can go from volume to mole, mass to mole, count to mole. And once we're at a mole, then we can go from any of the others. So we can go from a volume to a count. We can go from a count to a weight. We can go from a weight to a volume through our common term, the mole. See? Moles are fun. Moles are useful. And now comes the math. You knew it was coming. And now it's here. All right. In this section, section 3, we're going to discuss percent composition and chemical formulas, and we're going to calculate these using what we know already with the mole. So the math is not terribly difficult, but you will have to pay attention and remember these kind of basic procedures. Okay, so let's start with calculating the percent composition of a compound. Well, what is percent composition? Well, simply put, it is how much of the part is of the whole. What's the relationship of the part to the whole? So what percent of 92 is 42? So we would say, okay, 42, the part, how much of the whole is that? What percent is that? And so we would just make a fraction or a ratio. We would put the part over the whole and then multiply it times 100 to give us a percent. So in this case, if we put 42 over 92, it would give us 0.457. Multiplied by 100, it's 45.7%. So percent composition is simply how much is the part compared to the whole. We're looking for the relative amounts of an element, that's the part, in the whole or total compound. Okay, so how much does the part weigh compared to what the whole amount weighs? We're looking at the percent by mass of each element in the compound. And so here's what we're going to do. Percent mass of an element. It's going to equal the element's molar mass, that's the part, divided by the whole mass, the mass of the whole compound, and then we're going to multiply that fraction by 100%. Let's take an example. So let's calculate the percentage composition of magnesium carbonate. So the first thing we're going to do is we're going to find the mass of the entire compound. So we're going to take the individual masses and add them all up. So we're going to take a magnesium, which is 24.3 grams, and a carbon, which is 12 grams, and then 3 oxygens, which are 16 grams apiece. So for our whole compound, we have 84.32 grams. Now, we're going to calculate the percent of each one of these individually compared to the whole. So the whole, look, is going to be the same on all 3 of those. So for magnesium, we're going to take the weight of the magnesium over the whole weight. 24.31 over the whole weight times 100 gives us 28.8% magnesium. Then we do the same with the carbon. We take the weight of the carbon, the part, divided by the whole compound, times 100, 14.2%. Likewise, the oxygen, we have 3 times 16, which is 48. That's the part over the whole, times 56.9. And notice that these percentages all need to add up to 100%. Right, that makes sense because all 3 of these together make up 100% of the compound. Therefore, their relative percentages must total up to be 100. So that's a good check on whether you've done your math right. Now let's practice. Let's practice another one. Let's calculate the percent composition of propane, which is C3H8. So the first thing we're going to do is we're going to list the elements. We're going to count the atoms. So we have C and we have H. We have 3 C's and we have 8 H's. So we're going to multiply the number of atoms of each element by the atomic mass of the element, and we use the atomic masses from the periodic table to do that. We express each element as a percentage of the total molar mass, and then of course we check our answer to make sure, for example, that it makes sense, that it adds up to 100%. So let's do that. Okay, so propane, as you probably know, is the fuel commonly used in gas grills. To calculate its percentage composition, we're going to start with carbon. So carbon, there's 3 carbons, so it's 3 times 12. So the total amount of carbon, first we need the total amount of the compound. So we know that it's going to be 36 for the carbon and 8. So the total compound is going to be 44 grams. The percent of carbon is going to be the amount that's carbon, 36 grams, which was 3 times 12. Over the whole compound, 44 times 100. So it's 81.8% carbon. The hydrogen is 8 grams of the total, 44. Do the math, divide that, multiply by 100, we get 18%. And if we add those up, if we round this up to significant digits, we would get 82% and 18%, which together combine to 100%. Now, we can use percent as a conversion factor. So you can use percent composition to calculate the number of grams of an element in a given amount of compound. So let's remember back to the propane problem. We found that propane is 81.8% carbon. And remember that percent, the notion of percent means amount out of 100. Sometimes I like to think of it this way. A percent is like cents of a dollar. So if you have 83 cents, you have 83% of the dollar. So it's percent is the amount out of 100. So 81.2% is 81.2 grams out of 100 grams. So you can just assume, hey, listen, I'm dealing with a 100-gram compound for the total weight. 81% of that total is going to be 81.2 grams. So we can use that ratio, 81.2 grams of carbon per 100 grams of propane, to solve for the mass of carbon in a given amount of propane, say 82 grams. So let's say I've got 82 grams of propane, and I want to know how much of it is carbon. So I would set this up. I would say, well, I've got 82 grams of propane, and my conversion factor is 81.8 grams out of 100 grams will be carbon. So we have this many grams of carbon for this many grams, 100 grams of propane. So my grams of propane are going to obviously cancel, and I'm going to be left with grams of carbon, which is what I want. 67.1 grams of carbon. So if I start with a sample of propane that weighs 82 grams, and 80% of it is carbon, then 67.1 grams of it are going to be carbon. Does this answer make sense? Well, sure. 82% of 82, it's going to be, you're going to multiply 80 times 80, or 8 times 8, it's going to be 60-something. And that, so 67% would make, or 67, 66, 0.8 of 82 is going to be something in the 60s, and so that makes sense. Okay, now we can figure out how to calculate empirical formulas. So we can use percent composition to calculate empirical formulas. What is an empirical formula? Well, an empirical formula is the lowest whole number ratio of the elements of a compound. Say it again, it's the lowest whole number ratio of the elements of a compound. So it is, let's just look at, so a compound might have the empirical formula CO. Now, if that were also the molecular formula, we would call that carbon monoxide. But basically, we're saying that in this compound, my ratio of carbon to oxygen is 1 to 1. I have 1 carbon for every 1 oxygen. If, for example, it was my empirical formula was CO2, with a subscript right here, then for every 1 carbon, I would have O2. I would have 2 oxygens. And that would be my lowest whole number ratio of my elements to each other. Now, it's important to note that the empirical formula may or may not be the same as the molecular formula. As we're going to see, we're going to need to know the molar mass, the mass of the whole molecule, in order to know that if to check to see if our empirical formula is the same as our molecular formula. Sometimes it is, sometimes it isn't. One way to tell is that if you can cancel out equal numbers. So let's say you have a compound like C2H4. Let's say that's the molecular formula, C2H4. Is that the lowest whole number ratio of the carbons to the hydrogens? Well, no. C2H4, I could take a factor of 2 out of each of those. So I can reduce that to CH2. So CH2 would be the empirical formula, but it's not the same as the molecular formula, which is C2H4. Does that make sense? The empirical formula for hydrogen peroxide, for example. So the molecular formula is H2O2. But I can factor out a 2 out of both of those, right? So the lowest whole number ratio of H's to O's is 1 to 1. So if I were calculating the empirical formula for hydrogen peroxide, it would come out to be HO. And I would only know that that's different from the molecular formula if I know the molecular mass, if I know the mass, the molar mass of this whole molecule. Remember, it's just the lowest whole number ratio of moles of atoms. That's what we're comparing. That's what the empirical formula is. So, just to sum it up, empirical formula represents the smallest ratio of atoms present in a compound. The molecular formula gives the total number of atoms, not just the ratio, but the total number and kind of each element. So the total number of atoms of each element, so obviously it gives us number and kind, present in one molecule of a compound. Another way to think of it is the empirical formula is the simplest formula, and the molecular formula is the true formula. This is how the molecules form in the real world, in the natural world. The empirical formula is just the lowest whole number ratio of those elements to each other. So how do we determine the empirical formula? Well, the first thing we do is we assume that we're dealing with 100 grams of compound. Why? Well, because we're going to be starting with percent composition. So if I have something that's 80% oxygen, I'm just going to say, well, let's assume that I have 100 grams of the compound. If 80% of it is oxygen, that means 80 grams are oxygen. So we're going to base our calculations on 100 grams of the compound. And then we're going to determine the moles of each element in 100 grams of the compound. Then we're going to divide each value of the moles by the smallest of the mole values. Don't worry, this will make sense. But this plan of attack is important to know. And then finally, we're going to multiply each number by an integer to make all of these results of the division equal to whole numbers. Okay, an example will probably maybe clarify this. Okay, so let's say we analyze a compound and we find that it contains 25.9% nitrogen and 74.1% oxygen. What is the empirical formula for the compound? Okay, step one. We assume we're dealing with a 100-gram sample. Therefore, all of our percentages, 25.9%, automatically become grams. So 25.9% nitrogen becomes 25.9 grams of nitrogen. Okay, that's what assuming that we have a 100-gram sample does right off the bat. Then we're going to transform it into moles. So we're going to convert grams to moles. 25.9 grams of nitrogen times 1 mole per 14 grams gives us 1.85 moles of nitrogen. Okay, hey, so hang on to this for a second. Then we're going to do the same thing with our percentage of oxygen. We're going to convert our percentage to grams. So 74.1 grams of oxygen. Then we're going to convert that to moles as well. So we know for every mole of oxygen, it's 16 grams. So we can calculate, remember that we're creating conversion factors. We're going from grams to moles. And when we cancel our units, we get 4.3 moles of oxygen. Now, step 3, we divide all the quantities that we just got, 1.85 and 4.63, by the lowest number. Which one's the lowest? Obviously 1.85 is lower than 4.63. So we're going to divide both moles by the smallest number of moles. So 1.85 divided by 1.85 is going to give us, obviously, 1. So that's the red here. And 4.63 divided by 1.85 gives us 2.5. Well, wait, we need a whole number. So we're going to multiply both numbers by the same coefficient to get to a whole number. And the lowest coefficient that we can use is 2, because 2 times 2.5 will turn that 2.5 into a whole number 5. So we multiply them both by 2, the same coefficient. Whatever we do to one, we got to do the other. And that gives us 2 for the nitrogen and 5 for the oxygen. And those become our subscripts. So this 2 becomes the subscript for the nitrogen, N2, dinitrogen. And the 5 becomes the subscript for the oxygen, pentaoxide, dinitrogen pentoxide. So we started with percent composition and used that to calculate the moles of each, and then the smallest whole ratio number of the moles to each other. Okay, does that make sense? Let me go back to our plan. So start with 100 grams of compound, determine the moles of each element, divide each value of moles by the smallest of the values, and then multiply each number by an integer if you need to get a whole number, which is, in this case, we need to multiply both the 1 and the 2.5 by 2. How can we calculate molecular formulas, right? Remember, these give us empirical formulas that may or may not correspond to molecular formulas. So here's some examples. Remember, the empirical formula is simply the whole number ratio, the simplest whole number ratio of the elements. So in this one, we have one C to 2 carbons. I'm sorry, 1 carbon to 2 oxygens. Carbon and 2 oxygens. Now, when we compare it to the molecular formula, it turns out that that's the same. This empirical formula is the same as the actual molecular formula of carbon dioxide. The same with water. The empirical formula of water, 2 H's to each O, is the same as the empirical formula. But look at this. Here we have the empirical formula, 1 N to 2 O's, but the actual molecular ratio is a multiple of that. It's times 2. It's 2 N's and 4 O's. Notice the molecular formulas are always going to be a whole number multiple of the empirical formula. It's going to be times 2 or times 3 or times 5 or times some whole number. This is just the simplest ratio. This is the actual ratio. So it'll always be a whole number multiple that separates them. Here we have P2O5. The actual is P4O10. which is multiplied by a factor of 2. Here we have C5H11, the simplest ratio, empirical, but the actual ratio in nature is C10H22. C2H610, but actually it's 3 times that, multiplied times 3, it's 3 times 2 C's, so 6 C's, 18 hydrogens, and 3 oxygens. Here's some other examples where the molecular formula, the actual formula is C6H6, but of course that would reduce, if we're just looking at percent composition, to a 1-to-1 ratio. Acetylene is C2H2, but it also reduces to a 1-to-1 ratio. So look at this, the empirical formula for both benzene and acetylene are the same, which is why the empirical formula is of limited value, because here you might think, oh, we're dealing with the exact same compound because it has the exact same empirical formula. But when you get to the molecular actual formula, not so. They're very different molecules. So empirical formula gives you something, it gives you the simplest ratio, but it doesn't give you the molecular formula without an extra piece of information. And we're going to see that that extra piece of information is molar mass. Here's glucose, the actual formula. Here's the empirical formula. Water, we saw that that's the same on both. So how can we convert from empirical formula to molecular formula? Well, as I said, you have to know an additional piece of information. You have to know the molar mass, the total weight of the compound. And if that happens to be the same as the empirical mass, then you're done. Then the empirical formula is the same as the molecular formula. But if the molar mass is more, then you divide the bigger number, the molar mass, by the empirical, and you'll see that it comes out to a whole number. And if that number is 4, then the molecular formula is 4 times larger in every respect. So multiply every element by 4 to get the molecular compound. So the molar mass will either be the same as the empirical mass or some whole number multiple of it. Divide the bigger one, if it is bigger, by the smaller one. So here's an example. We know here that the molar mass of the empirical formula is 6 C's, 6 times 12, H7, 7 times 1, and nitrogen, which is 14, is 93 grams per mole. But the molar mass of the compound turns out to be 186.28. So what do? If they're not the same, you divide the bigger one by the smaller one. You divide the molar mass by the mass of the empirical formula. And in this case, you'll see that it turns out to 2, which means that the molecular formula is twice the empirical formula. So this number is this ratio. If this ratio is 2, we multiply the whole thing by 2. This 2 becomes our coefficient. We distribute this like math across all 3 of our terms. So 2 C6s for a total of C12. 2 H7s for a total of H14. 2 N's for a total of N2. And that is how you do it. So that is Chapter 7, Part 2, Fun with Moles. Thank you for your attention.